Thank you, Dave, and thank you for the invitation to come here today to talk a little bit about some of the research we have conducted recently in our team at the University of Illinois. So we will talk here first a little bit about net energy, the way we have determined it, and then after that, Aaron Gaines will talk about some of the work he has been involved in the industry where they have not determined net energy directly, but more productive energy and kind of determined what they get out of that. So that's what we will try to cover here over the next 25 minutes. So I will talk here for 22 minutes and then Aaron will sum it all up. Okay, so as some of you know, we have the ability at the University of Illinois to determine net energy using indirect calorimetry. And one of the studies we conducted there a couple of years ago was to determine the net energy in soybean meal. And there was a very specific reason why we chose to determine that. That's because in our digestible energy, metabolizable energy system, we have consistently over many years seen higher energy values than what the book values would indicate. So it was natural to say, do we get that in net energy? And you'll see here, yes, we did get a nice increase when compared with the book value. And the book value here is from NRC, and we had a greater value. And there was a similar study at the same time conducted in China, also with indirect calorimetry, and they actually got a little bit higher value than we had. So we repeated it, got the same value again, and then we thought, okay, maybe there's something in our system that doesn't work, maybe we don't understand how to use this, so let's try a different approach. So we looked at low protein diets versus high protein diets. And if you think about it, when you have lower protein in the diet, lower soybean meal, then you have more corn. And if corn has greater net energy than soybean meal, which it has according to our NRC book, then we should get a greater net energy value in a low protein diet. But as you can tell here, we didn't see a difference. No difference between low protein and high protein. So it didn't matter that we lowered soybean meal and increased corn, we still had the same net energy. Okay, so that would indicate that those two ingredients are more or less the same in terms of net energy. Okay, there was only 2 diets. Then we got more ambitious, said let's try with more diets, bigger changes. So here we had a control diet, high in protein because we had no crystalline amino acids in this diet, just corn and soybean meal. So there was 27% soybean meal in this diet. Then we had another diet with 19% soybean meal, more corn, and some crystalline amino acids, so we had it balanced. And then we gradually took down the soybean meal to 17, 14, 12, and 9%, and increased corn at the same time, and increased crystalline amino acids. And again, if you believe NRC, just calculating from NRC, we should see a linear increase in net energy in these diets as we reduced crude protein and reduced soybean meal. Right? That is what NRC would tell you. However, here are the net energy values. Absolutely no difference. Absolutely no difference between the low protein diets and high protein diets. And again, the only way to interpret this is that there's more or less the same amount of net energy in corn as in soybean meal. Right? Because it doesn't matter if you lower soybean meal or you have high soybean meal, lower corn, increased corn, same net energy, right? So that is what we got from the calorimetry unit. Then we thought, okay, maybe let's try another approach. Another way to determine net energy is to use what we call the slaughter procedure. And that means you kill some pigs up front, and then you have another group of pigs that you feed different diets, and then 4 or 6 weeks later you kill those pigs, and all the killed pigs you grind them up and determine the actual energy in the body of that pig, right? So you can see how much did the energy grow in those pigs. Those pigs you kill up front, you assume they are representative of all the other pigs, and then at the end you can see how they have changed over those 4 or 6 weeks. So we did that. We had four diets here. Again, a high crude protein diet just with corn and soybean meal, in this case 35% soybean meal. In corn, no crystalline amino acids. Then we added 3 crystalline amino acids, got soybean meal down to 24%. We added 4 crystalline amino acids, got down to 23%. And finally 5 crystalline amino acids and had 19% soybean meal. And corn increased as we reduced soybean meal. So same concept as before. It's just a different way of determining net energy. And results of this, there was absolutely no increase. If anything, there was a tendency for a decrease in net energy when we reduced soybean meal in the diets, right? So again, having a net energy in soybean meal that seems to be lower than in corn does not make sense, because it seems like when we reduce soybean meal, we do not see an increase in net energy, which we should. So when again, coming back to the book value, saying that corn has a value that's relatively high in net energy, soybean meal is 77% of that value. That's not what we see in these experiments. So you can start thinking about why is that? Why is it we have this discrepancy between book values? And by the way, it's not only NRC. It is the French, the Dutch, the Brazilians. They all have the same low net energy values for soybean meal, because all those numbers come from pretty much the same place. So that's why they all get the same conclusion. And where do they come from? Well, they come primarily from these equations. One of them is shown here from Noblet that he published in 1994. And what he's doing is, you can see he's starting out with the digestible energy. So he says net energy equals 0.70 times the digestible energy, and then he makes adjustments for the nutrients, therefore ether extracts, fat, and for starch. He adds a little bit if there's more ether extracts and starch in the diet, and then he subtracts something if there's crude protein, and he subtracts something if there's more fiber in the diet, right? And that's how those net energy values are calculated. And there's a lot of advantages to doing it this way. One is that by starting with the digestible energy, then he gets around all analytical problems with being able to analyze to 100% in the feed ingredient, because that's already included in that digestible energy value. So it's a kind of an adjusted DE system. But the important point here is you'll see the huge negative value he puts on crude protein, right? Saying that if you have more crude protein in the diet, then we will reduce net energy. And in fact, if you go to NRC again, you'll see there's actually a little bit more digestible energy in soybean meal than there is in corn. But because of that huge negative impact of crude protein, every unit of crude protein reduces net energy according to that equation, then you see this very low value for net energy in soybean meal. So it's a protein that drives down that net energy value. So then you can ask yourself, why did he come up with that huge negative value for protein? And unfortunately, he never published all the studies that led him to do that. He just said, I analyzed 61 diets, and this is the result of that. So we don't know what quality of soybean meal he used. We don't know what was the level of soybean meal. We don't know how he came up with that. He said this is the conclusion. He also published a paper where he said it can be assumed that nitrogen retention in a pig never exceeds 45 to 50% of absorbed nitrogen. This is absorbed nitrogen. So if you take nitrogen retention out of nitrogen in the diet, or protein in the diet, that would be 40 to 45% if there's 85% digestibility of protein. So he's saying nitrogen retention is only 40 to 45% of the nitrogen in the diet. And we've done a little bit of review of that, and his work was based on work in the 1980s. And it's probably true that in the 1980s, that was what we had. In the 1970s, you'll see lots of papers published where they had 32, 35% nitrogen retention. In the 1980s, 40, 1950s, 50. And today, in our pigs we have today, we are around 70, right? So that huge negative impact of crude protein that he put in the equation was based on pigs that were not as efficient in retaining nitrogen in the body. Today we have pigs that are much more efficient. You can see 70%. This is one experiment. Here's another experiment we conducted recently. Again, same thing. I just read a paper a couple of days ago from Brazil, and they were 65%. So not quite 70, but still a lot better than 40 or 45%. So my conclusion is that our pigs have changed, or we have become better at balancing the diets. Maybe, after all those computers we are using now are better than when we formulated by hand, which they maybe it did have an impact that we are better at it. So we are, in 1970s, we didn't have those computers. In 1980s, we started getting them, and it was not until late 1980s we had linear formulation programs. So maybe that has something to do with it also. Bottom line is, we retain a lot more protein in our pigs today than they did there back in the 90s. And I think that's one of the reasons why we have a greater net energy, because if we go from 45 to 70% retention of nitrogen, that increases the efficiency of the protein. And if we assume that all the amino acids, if there's 45% retention of protein, that means 55% of the amino acids have to be deaminated. And those 55% have an efficiency of only 58% on average. But the amino acids that are used for protein synthesis, they have an efficiency of 83%. So if you go from 58 to 83% for 25% of the protein, that increases net energy by about 163 kcal. And then on top of that, we have a couple of hundred kcal extras because the digestible energy is greater than what NRC is saying. So that gives us to 350 kcal more or less extra in the soybean meal we have today. So that is why we see that increased net energy. So in conclusion, we think, first of all, there's no evidence that low crude protein diets have greater net energy than higher crude protein diets, as I showed you here. We are pretty convinced about that. Modern pigs, they have greater nitrogen retention than older genotypes. I think I've shown you that also. And therefore, we retain a lot more of the nitrogen, of the energy in the pigs. And finally, we think those Noblet equations that we showed, that they may need to be adjusted, in particular for high protein ingredients. So those are the conclusions from the work we have done. Now, Aaron will talk about what he's seeing in practical production.
Sounds like I'm going to have to talk fast. I've got 3 minutes for conclusions. But we are going to switch gears here a little bit and talk about some of the observations we've seen in a commercial environment when it comes to soybean meal net energy value. And the story really starts back with some work that Dr. Dean Boyd did at the Hanover Company. In this first slide, they started off doing an experiment really to validate net energy estimates from the university. In the first study, they're represented by Boyd and Rush in 2018. That study was conducted in a commercial environment, but the environment was more like academic conditions in terms of stocking density, 8 to 9 pigs per pen, 300 to 400 pigs in that barn. In that study, they found a relative energy value of soybean meal to corn relative to corn NRC values on a dry matter basis of about 82%. And the good news from that first study was it was in very close agreement with the work of Dr. Stein in his lab, represented by Lee and others, within 1% of the university estimate. So they did a second confirmatory study. It's represented by Boyd and Rush in 2019. In that study, they got a little different result. In that study, they found a energy value relative to corn of 109%, so 30% higher than their first experiment. At the time, talking to Dr. Boyd, they didn't believe it, and so he did the best next thing, and they put that data into an archive, never to see the light of day until more recently. But that really was the first observation where we've seen this higher net energy value of soybean meal. I will point out in that second study, the conditions were more commercial-like in terms of pen density as well as pathogen load. Before I get into some of the other commercial conditions, I want to kind of go through the growth assay methodology that's used in these commercial experiments. It's a very simple growth assay. It's been used for 40 years to validate net energy estimates for feed ingredients, as well as to recalibrate equations, energy prediction equations. In the Han-Orr system, it's commonly referred to as the Snyder growth assay. You'll see that in some of our other publications. And that really goes back to Dr. Wes Snyder and one of his colleagues at Ralston Purina, where they developed that assay, and they used it extensively over the years. More recently, several companies, probably many of you in this room, have used a very similar assay. Dr. Stein mentioned it earlier. It's referred to as productive energy. And with productive energy, since we're measuring growth, that's really the amount of energy that's going toward growth in these growth assays. Again, it's very simple. You feed increasing levels of the test ingredient in relation to a known ingredient, like corn. And if your estimate is correct, as you increase the level, in this case soybean meal, if it's correct, caloric efficiency should be equal across those diets, so no change in slope. However, if there is a difference in caloric efficiency, either high or low, that means your estimate is not correct. And so you can do some calculations to correct that. Again, very simple methodology. So that moves us into another study. We had the opportunity to collaborate with some swine nutritionists from CP. Worked with Dr. Gary Stoner and some of their nutritionists on this project. Actually, one of the lead investigators is here in the room somewhere, Dr. Guao. So he's now with PIC, but he was very much invested in this work. We utilized the Snyder growth assay in 2 studies. The first study was a grower study, and the second study was a finishing study. 800 pigs, 4 different levels of soybean meal, 18 to 19 pigs per pen, so a commercial research facility. If we look at the results, the results are on a dry matter basis, and the values will be relative to a corn standard, and you'll see that in subsequent slides as well. So CP characterized the corn in this study quite well. And in the first study, again in grower pigs, what they found was a value of 110% of their corn standard in that grower pig. In the late finishing period, they found a relative energy value of 98% of corn. So this was encouraging, at least for Dean. He went back to the data archive and dug out the second Han-Orr study, because it looked like the soybean meal energy value was indeed greater under commercial conditions. We look at some data in the private sector. This is some work that was done in collaboration with Kansas State University and JBS Live Pork. It was reported by Samin in 2020. This was done in nursery pigs, about 6,000 total pigs between the 2 studies. In this study, they're referencing the soybean meal energy value back to NRC corn. In the first study, they found a relative energy value of 105% of corn. And in the second study, they found an energy value at 125% of corn. So when you look at these commercial estimates of soybean meal in practice, really looking at these commercial assays, again, the study by Boyd and Rush in 2018, yes, it was done in a commercial environment, but the conditions were more academic-like. They're in very close agreement with Dr. Stein's estimate at 98% of that estimate. Then you move to the other 5 studies, the Boyd and Rush study, the work by CP, and then the Samin study. We find a value that's about 31% higher than what Dr. Stein's lab reported. This doesn't mean that Dr. Stein's estimate is wrong. It's telling us under commercial conditions, when there's higher stocking density, perhaps more pathogen load, that traditional method of determining energy doesn't fully account for what's going on with soybean meal, and I'll talk more on that here shortly. But an important conclusion that we get from these commercial studies is the results are very repeatable. 5 studies, 4 location, 3 companies. And subsequent to this work, there's been a lot of companies, several of you in this room, that have looked at soybean meal energy value and have found similar results. And this doesn't apply just to health challenge pigs. It applies to commercial pigs in general. And so a question we get quite a bit is, what value do you use in practice? And so in terms of an energy value relative to corn on a dry matter basis, 90 to 95% is fairly common. However, we're seeing some corporate movement where companies have tested this for themselves, and they're moving that to 100 to 110% of corn on a dry matter basis. This next slide, this is an industry survey. What I did was basically polled some of the pork powerhouses. This is the top 11 pork powerhouses. These numbers are reported on an as-fed basis. It's about 2.9 million sows, so 49% of the industry. It kind of speaks to the consolidation that we have now. But on average, the average energy value relative to corn was 97%. You do it on a weighted basis, same thing, 97%, with a minimum value of 87% and a maximum value of 105%. I do want to point out that these differences could be influenced by the system's corn in terms of particle size, moisture content. We'll also point out that half these companies have done their own internal evaluations, which moves me into this next study. One of the pork powerhouses, the Mash-Offs, they've done a couple studies now looking at the soybean meal energetics. This is a USB project. They had 2,720 pigs, 20 replicates per treatment group, and then they looked at 2 feeding periods, an early and late finishing feeding period. And that early feeding period is from 90 to 150 pounds. Soybean meal level went from 21.6% in the low soybean meal diet up to 34.3% in the high soybean meal diet. If you look at the crystalline lysine levels in the low diet, it was 0.38%, and no crystalline lysine in the high soybean meal treatment. The late finishing period went from 200 pounds to a market weight of 295 pounds. The low treatment was about 11% soybean meal and went up to 21% in the high treatment. Once again, in that high treatment, no synthetic lysine. In the low treatment, 0.31%. I want to mention the health status on these pigs. They were PED negative. From a PERS standpoint, they were vaccinated positive, so 2V status, Delta Corona, myco negative. The assumption was they were SIV positive. Between the 2 studies, there was a washout period where pigs went on to a common diet. Diets were pelleted, and there's 3 dietary phases between the early finishing period, the washout, and the late finishing period. The diets were formulated to meet or exceed NRC requirements. And then from a formulation standpoint, going back to that growth assay, it's important to characterize the corn that you're using. And so in their case, they used Pioneer's NIR equation to derive the ME estimate, and then they made adjustments based on moisture and geometric mean particle size. For soybean meal, ME, they derived that using NRC values as a reference, and then made adjustments based on chemical composition using Noblet and Perez equations. These are a little small, but in terms of experimental diets, obviously graded levels of soybean meal, and soybean meal replaced corn and amino acids. In this particular experiment, they attempted to make the diets isoenergetic, so there was some slight adjustments in fat level coming from yellow grease in the study. So I want you to focus on the graphs first, and then we'll move to the table. But in both the early finishing and late finishing period, as soybean meal level increased in the diet, caloric efficiency improved, which tells us they were underestimating the energy value of soybean meal. When they went back and corrected that calculation in the early finishing period, they found an estimate of 102% of corn, and then in the late finishing period, a value of 103%. Also want to mention on their corn particle size, they're grinding corn at about 250 microns with a flow agent. So when I talk about these relationships, it's in relation to a fine grind corn. So in terms of the proposed concept for elevated soybean meal net energy value in practice, in this growth assay, we're measuring productive energy, or the total energy that's going toward growth function. And as you look at that, we can usually account for that productive energy through classical ingredient energetics like Dr. Stein talked about. But in the case of soybean meal, it appears to be different that way. If you look at the graph on the right, the blue bar there, by Boyd and Rush, we can explain about 75% of the energy in soybean meal from classical ingredient energetics. But there's another 25% that is not explained. And our current working hypothesis is that there's basically dietary net energy that's being conserved for growth, and that's likely due to some of the bioactives in soybean meal. And so as we think about productive energy in the case of soybean meal, it's the sum of classical ingredient energetics plus the sum of dietary NE conservation for growth. And it is different for soybean meal than other ingredients. And so I know Dr. Petrie in her presentation, she's going to talk more about those soy bioactives. So in conclusion, as we look at soybean meal net energy values under commercial conditions relative to NRC corn on a dry matter basis, it's at least equal to or 10% greater. And so if you want to put some values to that, we're suggesting a soybean meal net energy value 3,026 kcals, which would be equal to NRC corn, or 10% higher would be 3,328 kcals. You get into an academic environment or a situation where there's low population densities, lower pathogen load, 2502. And we went through several different data sets. It's been validated by other commercial pork production companies. In terms of the mechanism of action, that's not been fully elucidated, but right now the current working hypothesis is that the functional molecules in soybean meal are basically countering some of that pathogen diversion, and we're getting more conservation of that energy directed toward growth. Thank you.